This section in our notes is all about metallic bonding and why metals have the characteristics that they do. In ionic bonding, we discussed how cations and anions surround each other in a very organized structure called a crystal lattice. This three-dimensional structure is very similar to the structure that we see in metals. Since metals ionize to form cations, metals form a crystal lattice with cations and electrons rather than cations and anions. If you could imagine a large jar of M&Ms and you shake it and all the M&Ms have settled, you would see that each M&M is surrounded by many other M&Ms in close proximity to each other. Metal atoms do much the same thing. So, for example, a piece of metal has millions and millions of small, generally spherically shaped, positively charged cations, all stacked up tightly three-dimensionally. They are packed together so tightly that their outer electron orbitals overlap. This orbital overlap allows for the electrons to travel between cation to cation throughout the structure. Because of this overlap of orbitals, metals are considered to bond according to the electron C model. The electron C model proposes that all metal atoms in a metallic solid contribute their valence electrons to form a sea of electrons. The electrons are free to move around and are referred to as delocalized, as in they do not stay in one localized place. So this forms metallic cations surrounded by moving electrons. A metallic bond within the sea of electrons is the force that holds metal atoms together. For example, in a sheet of copper, it is the force that holds the copper atoms together in a structure, but it is not the attraction between one copper cation and another copper cation. Rather, it's the attraction between the cation and all of the delocalized electrons in the structure. You can kind of consider the delocalized electrons as the glue that holds the cations together. This interaction, just like an ionic lattice, is very strong. It is very, very difficult to remove cations from this sea of electrons. Because of the way metals bond and the extreme attraction between the cations and delocalized electrons, we see characteristics that reflect the strength of this structure. For instance, boiling points are much more extreme than melting points because boiling points are actually separating the cations from the sea of electrons. Melting points, though, only allow for the cations to move around within the structure, and while they are high, they are not extreme. Another property of metals is that they are malleable and ductile. In other words, they can be hammered into sheets and drawn into wires. They have this ability because the crystal structure can shift and still have the delocalized electrons to hold the structure together. And again, these delocalized electrons can be viewed as kind of the glue that holds it all together. So most metals can be formed and morphed into different shapes. And finally, one of the most important properties of metals is their ability to conduct heat and electricity. Since orbitals overlap within the structure, electrons can travel. These mobile electrons around cations make metals really good conductors of electricity and heat because they can carry energy and charge throughout the structure. As the number of delocalized electrons increase within the structure, so does the hardness and strength of the structure. Within the metal structure, we can also mix metals. These homogeneous mixtures are called alloys, and the properties of alloys are always different than the elements in which they contain. Again, they're kind of like ionic compounds that way. The individual atoms do not necessarily determine the property of the compound. I included a table of some common alloys here, and you are probably familiar with many of them, such as brass, bronze, sterling silver, and even 14-karat gold. These are all mixtures of metals. There are two types of alloys, substitutional and interstitial. Substitutional alloys are formed when some of the atoms in the original metallic solid are replaced by other metal atoms of a similar size and similar atomic structure. Interstitial alloys, on the other hand, are formed when small holes in the metallic crystal are filled with smaller atoms. If you look at the picture for substitutional alloy, you will notice that some of the atoms are replaced with others of similar size, like the combination of copper and zinc, which creates brass. Copper and zinc are next to each other on the periodic table and therefore are similar in size and can be substituted for each other within the structure. Examples of this type of alloy are brass, bronze, sterling silver, and 14-karat gold. The second alloy picture is interstitial. Notice that this mixture of atoms are of different sizes. A good example of this is steel. The larger iron atom creates the main lattice, the main structure, and then carbon, which is a far smaller atom, fills the spaces in between the iron atoms. This strengthens the structure and prohibits some of the movement that we see in most typical metal lattice. This is why steel is stronger and less malleable than iron by itself. This concludes our video for metallic bonding.